Hey, see, perseverance pays off. Huzzah! Okay, so we're gonna meet the last, kind of a bittersweet day. We're gonna meet the last of our identities today that we are responsible for, not just knowing, but memorizing, or I should say, not just memorizing, but knowing. Right? That's maybe a little bit higher burden there. They're called the power-reducing identities, or the Kryptonite identities, if you want to think about it that way. Reduce the power, sap the power out of something. Not necessarily that sense of power reducing, but in this case, we are going to be taking squares, things that are raised to squared powers, and we're going to reduce the power down to single powers, okay? So we're going from 2 to 1. We're going from 2 to 1. So we can write sine squared as a single power of cosine. If you notice the next one, we can also write cosine squared as a single power of cosine. And of course, because we always have our ratio identity, we can write tangent squared in terms of single powers of cosines. This one you don't have to memorize, because this one, as I'll show you here in a second, is just sine of x over cosine of x. Okay, cosine of 2x, sorry. Cosine 2x and sine of 2x. Okay, so if you need to memorize these, here's how you can kind of help yourself. Notice the sine squared and the cosine squared look very, very similar, don't they? The only difference is the plus and minus sign between them. Now, when we do the composite identity, we say sine, same sign. But because everything here is in terms of cosine, cosine, being selfish, has his way. And so he decides that he is going to be positive, or at least take the positive sign. You know, greedy, selfish people, just because they say they're going to be positive, that doesn't make them a positive person. Cosine is still, I said persine. That's funny. Doesn't make them a positive person. They're just claiming it for themselves. And sine being like, whatever, it's okay, cosine, I'll pick up the negative, no big deal. Now, when you do the tangent squared, you just do the sine squared, and you divide it by the cosine squared. So what happens to the 1/2 when you do that? When you take the sine identity, which has the minus sign, and the cosine identity, which has the plus sign, the 1/2 divide out. Okay? So that's why you don't need them. All right, so why do we need these power-reducing identities? Well, if you're going to take calculus BC especially, or calculus next year in college, or maybe you're taking calculus in the juice aisle or something at HEB, which, you know, nowadays you can, right? You could be in the juice aisle at HEB on your phone watching Corpy's World taking calculus, or taking, Harvard has online curriculum that's free. MIT has free online curriculum. You can learn anywhere now, right? It's amazing. Okay, you might be wanting to reduce the power. Here's a real quick motivation for those of y'all taking calculus BC next year. Let's say we have the graph that looks something like this. Okay, and you don't have to worry about the equation. We call that a cardioid. It's a heart graph, and it would be of the form r equals, let's just say 2 plus 2 cosine of theta. Okay, we're going to try and find next year in calculus the area of that. Well, there is no geometric shape for the area of that. So what we do in calculus is we kind of think about, okay, can I just take little sectors from the origin here? Do you remember earlier in the year when we did our Freudian pizza? Okay, if I wanted to figure out the area of a sector of a circle with a central angle of theta, what was the area of that sector? Do y'all remember? Y'all should remember. There was a formula for the area. Remember? What's the surface area of the slice of Freudian pizza? Come on, anyone? Brain. 1/2 r squared theta. 1/2 r squared theta. Very good. I knew it would come back to y'all. Well, in calculus, we can approximate the area by taking little arcs that are circular. Okay, so notice in this case, if I find the area of each of these little bitty sectors, I can figure out and add them together. I can get an approximation. Now, it's not going to be the actual approximation because, of course, we're missing some parts right there. And we can do that all the way around to get an approximation. Well, what if you wanted to get a better approximation? What could you do? You could take twice as many, right? And now when you take twice as many, you're minimizing the error. See that? Because now you're picking up this and this and this. So the more little sectors that you use, the less error there is, okay? Well, the idea is if you can use infinitely many of those and add them all up, you'll get the actual. And so that's where the calculus comes in. We would say then, using the formula for the area, instead of taking what we call a delta theta, which is a change in theta, like delta x, delta y, this is a measurable change in theta. In calculus, what we do is we let it be d theta, which is infinitely small, immeasurable. And then the way we add them all up is like this. We take what's called the integral, and it looks like an S symbol, okay, for a good reason. It means sum, okay, and so that's why it looks like an S. If we add up all of the little sectors from A to B of your 1/2 r squareds, and instead of theta, it's d theta, that is a way to get the area of these regions, okay? D theta is infinitely small, and the integral symbol is what we use to add up infinitely many of them. Now, in order to do that, we would need to plug this equation in right there and evaluate it. Well, when we square multiply double squared, we're going to be staring at a cosine squared. And if you want to evaluate what's called the integral of a cosine squared function, guess which identity you're going to have to use? You're going to have to use the power reducing identity, which allows you to express a squared angle, or a squared function, sorry, in terms of a single function, okay? Super important, all right? So let's try them out right here. You do have to memorize these, and it would be good to kind of maybe have like a pop quiz tomorrow over just regurgitating all the identities, right? It would only be a pop quiz if you didn't prepare. Okay, so let's go ahead and write sine squared cosine squared in terms of a single power of cosine, just to kind of get a feel for using these fellas. Okay, step one, I got sine squared times cosine squared. I want to write it as a single power of cosine, so something of the form like a cosine to the first of bx, something like that. I don't want any squareds, and I only want cosines, sorry. Now, if you use the papa pids here, replace sine squared, excuse me, with 1 minus cosine squared, or cosine squared with 1 minus sine squared, you're still going to end up with sines and cosines. So I wouldn't go that route. If you're trying to write it as a single power, and we have a double power, we need to use the power reducing identities. Now, here's a good way to think about the power reducing identities, okay? You can half the power, comma, by doubling the angle. That's kind of a nice way to think of it. It's kind of a trade-off. So we started off with a 1x, but when I halved the power to get a single power, I had to double the angle, okay? Half the power by doubling the angle. It's the trade-off. Reduce by a factor of 2 the exponent, increase by a factor of 2 the angle, okay? Sine squared, cosine squared. All right, so let's go ahead and use the power reducing identity. Sine squared is 1/2 times 1 something cosine of 2x. Notice they're both in terms of cosine. Is the sine squared going to be plus or minus there? Minus. So in this case, the sign changes, right? Cosine was selfish because everything in terms of him, he chose the positive. Times the cosine squared is 1/2 times 1 plus cosine of twice the x, which is 2x. So there is the replacement. Okay. Now those outside parentheses, the pinks and the greens, that just shows the substitution. We can start combining things now. This is 1/2 times 1/2. We can actually multiply those together and get 1/4. And then we have 1 minus cosine times 1 plus cosine. And those are what's of each other? Conjugates. So when we expand that out by Forlane, we get 1 times 1 is 1. The inner and outer are going to cancel. Minus cosine 2x plus cosine 2x. I'm not going to worry about that. And then the last term we're left with negative times positive is negative. Cosine times cosine is cosine squared of 2x. Now at this point you can use the power reducing identity again on cosine of squared of 2x, or you can make things easy for yourself. Okay, get rid of 2 terms and put it in terms of 1 term. What is another name for 1 minus cosine squared of anything? Sine squared. Yeah, it's using papa pid. The angles don't have to be always single x's. As long as they match, you're good. 1 minus cosine squared of 100x is equal to sine squared of 100x. So in this case, 1 minus cosine squared of 2x is sine squared of 2x. Now I still have a higher power there of 2. So I'm going to use the power reducing identity once again. 1/4 is just kind of hanging out front. And here we go. The sine squared becomes 1/2 times the quantity 1 something cosine of twice the angle. So in this case, if we start with 2x and double it, what happens to the angle? Becomes a 4x, yeah. And of course, what is the SIGN sign between those two? Because it came from a sine? Negative, right? Good. All right, now, we're almost there. Pretty close. That's just a 1/8 times 1 minus cosine of 4x. Or if you distribute a 1/8 minus 1/8 cosine of 4x. Either one of those I would consider to be equally simplified. But notice it is a power, single power, cosine to the first of some angle. All right, so that bottom expression, believe it or not, is a lot easier to work with than the sine squared times cosine squared. And they are mathematically the exact same. Now, here's one last thing I want to show y'all on this section before we get to the next identities. Where do these power-reducing identities come from? France? Marshmallows? I don't know. Actually, I do know. Let's look at cosine of 2x, just kind of on the same example, go off to the side. What was the cosine of double angle 2x I told y'all to memorize? Cosine of 2x it is. Everyone knows it. You're just being shy and bashful. Good. It was the Elvis impersonator. It's Papa Pitt impersonator. Cosine squared minus sine squared. And remember, there were 2 other versions that you didn't have to memorize because they come freely. All right? So here's what I mean by that. If I want to put this in terms of cosine exclusively, let's put parentheses around the sine squared and replace it with what it's equal to in terms of cosine. That's 1 minus cosine squared. And now if I distribute the negative, I get cosine squared minus 1 plus cosine squared. And then if I combine those two like terms, I'm going to write this left side down again. Cosine of 2x is equal to 2 cosine squared of x minus 1. So that's one of the other 2 versions. And again, you don't have to memorize that version because it comes so freely and easily from Papa Pitt. Now notice, if I want to solve this for cosine squared, all I got to do is add 1 to both sides. So I get cosine of 2x plus 1. I'll add it like that. And that should equal 2 cosine squared of x. And now to get rid of the 2, I'll multiply both sides by 1/2. The complete both sides by 1/2. It now divides out on the right. And I'm left with cosine squared equals 1/2 times 1 plus cosine of 2x. Do y'all recognize that from anywhere? Yeah, that's our power reducing identity that we just used. So where does it actually come from? It literally comes from the double angle for cosine, just by manipulating it a little bit algebraically. So I guess in theory, you don't actually need to memorize the double angle for cosine because it comes from the composite identities. But we use it enough that you do memorize it. Same thing, you don't have to memorize the power reducing identity for cosine because you could derive it every time you need it from cosine of 2x. But some things are best not to reinvent every time you need it, right? Like the wheel, right? When you need to go somewhere, you don't like, well, let me reinvent the wheel so I can get over there by rolling something, either in a car or a bicycle or, you know, there's some weird unicycle people out there that go places on the unicycle. But anyway, it's round. You don't want to have to do that. You're just like, oh, the wheel's already invented. Let me just get in my car and go. Same thing here. You just want to memorize that because it shows up enough. Now you can also easily do the same thing, put it in terms of sine squared by replacing cosine squared with 1 minus sine squared, and that's how you develop then the power reducing for sine squared. They both come from the double angle for cosine. So kind of neat, okay, kind of neat. We're just kind of progressing. All right, so this all builds up to the last set of angles that y'all have to memorize this year, and these are the fun ones. Okay, these are the fun ones. I enjoy these. I think y'all will too. All right, the half angle identities, the last set of the year. Now, like the double angle identities that allow us to express an angle that is twice as big in terms of something that's smaller, the half angle identities allow us to express something that is half as big in something in terms of something that's larger. So sine of 1/2 of some angle x can be expressed in terms of single x, an angle that's twice as big. Okay, we start with a small angle now, not a bigger one, but a half angle, and I could express it in something that's twice as big. So it's equal to plus or minus the square root of 1 minus cosine x over 2. Or we can write that equivalently. This is kind of the way I prefer it these days. 1/2 times 1 minus cosine. Pulling the 2 out from the denominator and putting it as a 1/2 in the front. Okay, do you kind of recognize that from anywhere? You have a sine, and it ends up being 1/2 1 minus cosine. Interesting. Similarly, cosine of 1/2 x can be equal to plus or minus the square root of 1 plus cosine over 2, or as I like to call it these days, plus or minus the square root of 1/2 times 1 plus cosine. And again, notice there's some similarities here. We have a cosine and a 1/2 times 1 plus cosine. That's interesting. Now notice the plus or minus there is kind of like, whoa, what is that all about? Well, it's there for you to ultimately decide when you use it which sign it's supposed to be. Okay, you must pick the sign. Okay, and it says right here, depending on the quadrant in which the half angle x terminates. So you're just going to have to figure out, okay, if I'm taking sine of some angle in that quadrant, is it supposed to be positive or negative? And if it's supposed to be positive, you assign the plus sign. If it's supposed to be negative, you assign the negative sign. Okay. Now the last one here is tangent of 1/2 x. And again, you don't have to memorize anything new because it's just the sine over the cosine. If you took this sine right here and divided it by this, you can put them under the same radical. Your 1/2s will essentially divide out. Okay. And that's why you get that one right there. Okay. So these are the fun ones. And let me show you an easy way to help remember them. These right here don't come from France either. Let's look at the cosine one again. Let's look at cosine squared of x equaling what? What was the half angle power reducing identity? Sorry. Cosine squared was 1/2 1 no plus cosine of 2 times x. If this is 1x, this is 2x. Cosine gets his name on all of them, so he claims the plus sign. Okay, I'm going to do a little substitution here. Notice that the angle on the right is 2x. It's twice as big as the angle on the left, x, yes? Or the other way around, the angle on the left, x, is half as big as the angle on the right, 2x. That's the thing we need to preserve. But here is what I'm going to do. I'm going to say let u, some dummy variable, some arbitrary variable, let that equal 2x. Okay? If I do that, then the right side becomes 1/2, 1 plus cosine of not 2x, but what 2x is equal to, u. Well, on the right side then, to keep it the same, I need to solve for x. So if I solve that for x is going to equal 1/2 of u. So this becomes cosine squared of 1/2 u. And notice the relation, the linear relation between the two is still the same. The angle on the right, u, is still twice as big as the angle on the left. And the angle on the left is still half as big as the one on the right. Well, now, if I solve for cosine of 1/2 u, I will unsquare both sides. How do we unsquare both sides? Square root. So that's cosine of 1/2 u equals, now when we take the square root, we have to consider what? Both plus or minus the square root of 1/2 times 1 plus cosine of u. And now at the end, because u is just an arbitrary variable, we can let any variable equal that, as long as the pattern is the same. The angle on the left is half as big as the angle on the right, or the angle on the right is half or twice as big as the angle on the left. So we could replace that back with x again if you want, without any loss of generality. That's 1/2 times 1 plus cosine x. And that you should recognize as the power or the half angle identity for cosine. So let's do this. This is kind of neat. The double angle identities, they come from the composites. The composite identities give us the double angles, right? By letting both the angles equal x plus x, all right? And then from the composite identities, these come from the composite identities, from the cosine of 2x composite identities, we get the power reducing identities. And then these, from the power reducing identities, just manipulating them, we get the half angle identities. So they're all just kind of maybe evolutions, if you want to think about it, or different useful versions of the same identity, right? Like when we multiply by a clever form of 1. It's nice to have different versions of 1 to use. Okay, let's try one out, okay? I think you'll pick up on it. Example 6, find the exact value of sine of pi eighths. Let's do that first. Now, sine of pi eighths, you're saying, okay, pi eighths is not on the unit circle. Well, what the half angle identities allow us to do is to get exact values of anything that's a pi eighths or what multiple? How many degrees is pi eighths? Y'all know? Well, let's see. Pi fourths is 45 degrees, right? Pi eighths is half of pi fourths. So what's half of 45? 22 and a half. So just like with the composite identities, we can find the exact value of anything that's something pi twelfths, right? A multiple of 15 degrees using the composite identities. That expands our unit circle knowledge. Now we could do it with anything that's a multiple of pi eighths or a multiple of 22 and a half using the half angle identities. Isn't that awesome? I know, rhetorical question, right? The answer is, of course, yes. Let's try it out, okay? So we know that sine of blank pi eighths, that's not reducible, can be written as 1/2 times another angle. So that's your first step, right? Sine of pi eighths is 1/2 of something. Well, pi eighths is half of what? Pi fourth. Yeah, you just factor out a 2 from the denominator. 8 is 2 times 4, so as long as it's, it's 8, it's always going to be 2 times something. All right, so now, using the identity, I can say that that is equal to plus or minus the square root of 1/2 times 1 plus or minus cosine, I can't remember what it is, but we'll come back to it, pi fourths. And of course, what is the SIG and sine between those when it comes from sine? A negative. Now, the sign out front, plus or minus, we need to figure that out. So think about pi eighths. In which quadrant does pi eighths live? 1. It's like 22 and a half degrees. It is half of pi fourths. In quadrant 1, is sine of pi eighths positive or negative? Positive, right? In quadrant 1, all of them are positive. So we're going to go with the positive square root in front. Had that been like sine of 11 pi eighths, that would have been in quadrant 3, that would have been a negative. So just like we're used to figuring out where angles terminate, we just have to then know, all right, in that quadrant, is the sine of the cosine positive or negative? All right, so that's how we get the sine in the front. Once we use the identity now, we can evaluate it using the unit circle. So this becomes 1/2 times 1 minus, and cosine of pi fourths, of course, is square root of 2 over 2. Now here we get an exact numeric answer. But that's not good enough. The fun now begins. The fun now begins. Okay? Because what we want to do is simplify these expressions. And here are the rules. Number 1, the first rule is no fractions under a radical. That's the first rule. No fractions under a radical. Number 2, no radicals in the denominator. No radicals in the denominator. All right, and then number 3, it should be expanded out. That means multiplied out. Not factored. That's just kind of a general rule. But to guide you, the first 2 should be important. No fractions under a radical and no radicals in the denominator. Got it? So let's start coming up here and you're like, hey, I got a radical under a radical. That's not necessarily bad, but I do have a fraction under a radical. That's no good. So here's what you're going to want to do first. The first thing that you could do is distribute the 1/2. Okay? And that's going to be pretty much universal. That gives you a 1/2 minus the square root of 2 over 4. Now make sure that this radical here, the outer one, goes down long enough so that it covers your denominators. All right? If you chopped it off short like this, you're going to lose points because that looks like only the numerator. So make sure that radical kind of encompasses everything like that. Your radicals should always cover exactly what they need to cover. No more, no less. All right, so what that allows me to do then is to get a common denominator, which is your next step. Well, don't do your crisscross applesauce here because it'll give you a common denominator of 8. The LCM of 2 and 4 is 4. So just think of 1/2 as 2/4. So what is 2/4 minus square root of 2/4? Well, it's 2 minus the square root of 2 over 4. So distribute. That's kind of the annotation. And then get a common denominator and combine. Okay, now that we have that, now we can use this little property. The square root of a over b, of course, is equal to the square root of a over the square root of b. We can give each numerator and denominator their own radical because I still have a fraction under the radical. So that becomes the square root of the numerator all over the square root of the denominator, like that. Okay, and I can only do that because it's a single term. And now what's the denominator? What's the square root of 4? 2. So all of that could be over 2. And here you could stop. It's okay to stop there. That's good. There's no fractions under a radical. We have a 2 under a radical and a square root of 2 under a radical and a square root of 2 under a radical. And we have no radicals in the denominator. But we still do have a denominator. So the preference that I have, which is fine to leave it like that, is to bring the factor of 2 out front and call it 1/2. Okay, that just looks better. Okay, looks better. Because now you don't have a denominator at all. Bless you. But either one of these would be okay. So notice we do have a radical under a radical. And that's going to be usually the case when we have these half-angle identities. Okay? So pretty nifty. All right, I want y'all to do a cosine of 7π8 on your own. And let me get you started. That's the same as cosine of what? 1/2 times what? 1/2 of, just factor the 2 out of the bottom, right? 7π4. So go ahead and use the cosine identity. I'll give you a minute or two. And then try to simplify it using the same kind of strategy that we just did. No fractions under the radical, no radicals under the fractions, and make sure it's fully expanded or multiplied out. Y'all have it written down? Yeah. I'm just going to verify the previous problem while y'all are working. Again, if you're stuck, right, here's all we did. We just wrote it as 1/2 of 7π4. Just factor 2 out of the bottom. All right, sine of π8 is that. And the exact answer we had was 0.5, 1/2 times the square root of 2 minus another square root of 2. It's easy to verify these things on the calculator now with math print because you could see your radicals. All you got to do is click to the right to get out of your radicals. But back in the day with classic print, you had to use parentheses, and it got pretty confusing. But there's your confirmation of the previous example. They're exactly the same. All right, maybe you're either stuck or on your way to getting stuck, or maybe you're getting closer. I do want to point out one thing on the previous one. When we take sine of pi eighths, that's half of pi fourths, right? We got the same answer when we actually just type in sine of pi eighths. The calculator gets this answer from a very different method than evaluating 0.5 square root of 2 minus square root of 2. But the way its accuracy level is right on, okay? Now, if you were to just take the sine of pi fourths ratio, square root of 2 over 2, and take half of it, you don't get the same thing as half the angle, okay? So to get the sine value of half the angle, you can't just take half the ratio of the bigger angle, okay? Because the sine of the half angle is 0.38, and then half of sine of pi fourths is 0.35. So if you looked at the graph right here, of course, pi fourths is square root of 2 over 2. That's the brown version right here. That's just the square root of 2 over 2. And when we take sine of pi eighths, because the graph of sine increases at an increasing rate, it's a little bit above half the ratio of pi fourths. So you can't just take, sine of pi eighths, that's sine of pi fourths, and then divide by 2. It doesn't work that way, okay? You have to actually use the identities. All right, so let's pick up where y'all were on the cosine one, and then I have a little bonus extra one for y'all that's going to make your day so much warmer, okay? It was like 54 degrees at my house this morning. That was beautiful. It's like, yes, more of that, please. And the sun was coming out, and the birds were chirping. All right, so here we go. We get cosine. Oh, well, we already have that. Let me just go straight to the next line. We get 1/2 times 1 something cosine of 7 pi fourths. Okay, so is it going to be plus or minus? Plus, good. So we get down to that, and now we just evaluate, okay? Oh, I forgot my square root. Sorry, don't forget the square root. Is the square root in front plus or minus? That's an important thing. So before you go, as soon as you write it down, it should be plus or minus. Where is 7 pi eighths located? It's in quadrant 2, right? That's 7 pi eighths, because pi, remember, is 8 pi eighths. So we're 22.5 degrees short of the x-axis. So anytime you have something pi eighths that's irreducible, your reference angle is going to be a multiple of 22.5. All right, so in quadrant 2, is cosine positive or negative? Cosine is negative in quadrant 2. So we need to have a negative in front of the radical. Okay, from the very beginning. Don't put plus or minus to begin with. You have to commit to plus or minus in the very beginning. All right, so that should be step 1. Now, once we get it set up with the identity, you can evaluate it. Cosine of 7 pi fourths is different. Where is 7 pi fourths listed? Quadrant 4. And in quadrant 4, it's what? Positive or negative? Positive. Cosine's positive there. Okay, so you got to be very careful. The half angle out front is a negative because it's in quadrant of 2. But when we evaluate cosine of 7 pi fourths, it's just the way we've always done it. It's positive square root of 2 over 2. And now that you get down to this ratio, you got to bring the negative along every time. Now it should be kind of the same. You'll see that it works out the same pretty much every time. 1/2 times the square root of 2 over. Oops, I wrote square root of 2 over square root of 2. That doesn't work. Haste makes waste sometimes. 2 times 2 is 4. And again, if you need to kind of extend that radical down a little bit right here at the crotch where it pinches, see that? We call it the crotch or the V or whatever. Yeah, crotch is like, I don't know. But trees have crotches too. And I guess so do pants. We extend that down so it looks like it's on the same ground floor as your denominator. Now we get a common denominator, which is 4. So we get 2 plus the square root of 2 all over 4. And then we give each the top and bottom their own radical, and we're almost there. So now the square root of 4 is 2. We pull the negative out front, and you notice that it looks very similar to the other one in its final form. And it will. It'll always kind of look very similar to that. And there's your answer. If you want to type it in, you can verify that they do give you the exact same number. Okay, so get used to having radicals on the radicals, but make sure that your radicals extend only over what they're supposed to, including the radical symbol, okay? And your horizontal division bars, make sure it's covering all of the fractions it needs to, so on and so forth. Oh, yeah. I distributed. Where did it come from in the beginning? Oh, I skipped that last little step. I just 2 plus square root of 2, and then in the bottom, what is the square root of 4? Yeah, it's 2. Yeah, and then I bring the 2 out front and call it a negative 1/2. So if you want to, again, if you want to show that step before you get to 1/2, or if you want to leave it, either of those are good as final answers. I'm okay with either of them, as long as there's no radicals in the denominator. 2 is not a radical, and as long as there's no fractions under your radical, and as long as it's expanded, there's really nothing left to expand. We can't distribute anything, okay? So your final answer should look like that. All right, any other questions before we move on to a bonus fun one? Brighten your day. It gets real interesting when we start looking at tangent. So let's look at tangent. Let me think. Let's just do tangent of 11 pi eighths. Okay. Now we know 11 pi eighths is not on the unit circle, but because it's something pi eighths, it's going to work. Okay. So here's where you got to have some fun. This is the same as sine of 11 pi eighths over cosine of 11 pi eighths. So that's just using the ratio identity. And now each of those you can write as 1/2 of something. That's 11's too big. Let's just make it smaller. I just made that up in my head. I wasn't thinking of the consequences. Let's do 9 pi. No, let's keep it even smaller than that. Let's just do pi eighths. Let's just do single pi eighths. That way we can kind of get in the mood for bigger and better problems. We'll work the easy one first. So let's just call that pi eighths. So that's sine of 1/2 pi fourths all over cosine of 1/2 pi fourths. Now if we expanded out the numerator, we're going to end up getting the same thing we got over here on part A. But let's just work it out again anew. All right, so now we'll use both of the identities. We come up here first because we have a square root in the top and a square root in the bottom. And I need to know if they're positive or negative. Well, tangent of pi eighths, that's in quadrant 1. Again, and in quadrant 1, tangent, as all trig functions are positive. So that's positive, positive. So we got the sign on our radical. Pi eighths lives in quadrant 1, tangent there's positive. So now we use the identities. In the top we have sine, so that's 1/2 1 minus cosine of pi fourths. And in the bottom we have cosine. That's 1/2 times 1 plus cosine of pi fourths. So again, remember, we're not memorizing anything new for the tangent. We're just doing the sine over the cosine. All right, so from here, what we can do is we can put them under the same radical. So that gives us 1/2 1 minus cosine of pi fourths all over 1/2 times 1 plus cosine of pi fourths. And again, that's using the rule that says the square root of a over the square root of b is equal to the square root of a over b. Now, by putting them under the same radical, and again, we don't have to write the plus sign out front, what happens to the 1/2s? They divide out, yeah. So we're left with just 1 minus cosine over 1 plus cosine. Now, let's go ahead and evaluate it. I saved it so I wouldn't have to write so much, but now it's time to evaluate it. Cosine of pi fourths is the square root of 2 over 2. So both of those become square root of 2's over 2's. And now we can start working on the rules. No fractions under a radical and no radicals in the denominator. All right, so at this point you can work in the top and bottom like we did when we worked them individually. There's no 1/2 to distribute, but you could still get a common denominator, which is 2. So call 1 2 over 2, okay? Call 1 2 over 2, and you get 2 minus the square root of 2 over 2, and on the bottom you get 2 plus the square root of 2 over 2. And again, this outside square root goes all the way down to the bottom there. Fun, 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 fun. And now from here something cool happens. What happens to your 1/2s? Or these 2's in the denominator? They what? They divide out. Yeah, that's off to the side here. I'll say what's happening. 1/2 divided by 1/2 equals 1. So we're just left with 2 minus the square root of 2 all over 2 plus the square root of 2. So it simplifies down to there. Having fun yet? Oh, yeah, right? Jimi Hendrix did this on the side. This was his recreation, along with Karl Marx. Both did math for recreation. All right, so now what we can do is we can go back to this little one up here, and we can give them each their own radical again, because now we've simplified as much as possible. So if I give them each their own radical, we get 2 minus the square root of 2 all over the square root of 2 plus the square root of 2. Now at this point you might think, are we done yet? And the answer is no. Now the fun begins. Now the fun begins. We don't have any fractions under our radicals anymore, do we? But notice in the denominator, we have 2 radicals, and that's not good. So now we're going to start rationalizing. Okay, now we start rationalizing the denominators. All right, so step 1. I have a square root of a something, just a single square root. It's one term. So remember, if we had like 1 over the square root of a, we would rationalize it by multiplying by the square root of a over the square root of a. No conjugates yet, right? Just radical over radical. So that's what we're going to do here. We're going to multiply the bottom by the square root of 2 plus the square root of 2, and the top by 2 plus the square root of 2, because it's a single radical. Now, in the denominator, we always want to do that first. What is the square root of something times the square root of the same something? It's that something, right? It's the radicand. So we get 2 plus the square root of 2. Yeah.
Whenever you're doing conjugate over conjugate,
I didn't do conjugate over conjugate. I'm just doing radical over radical. Because I pretend like I don't even see the 2 plus the square root of 2 yet. All I see is the square root of blob, right? So like this, if I have the square root of a blob, I just multiply by the square root of blob over the square root of blob. It's one term. Okay, but when I do that, what is the square root of a times the square root of a? It's just a. Okay, so I'm just left with my a, if you will. Okay, that's essentially what we did. Now in the top, notice this: the square root of a times the square root of b. That's the same as the square root of a times b. So because they're both square roots now, I can multiply those two fellas together underneath the same radical. See that? I knew you would be liking this. Right here? Oh yeah, it's supposed to match the bottom. Thank you. Yeah, thank you. Yeah, there you go. Very detail oriented. Good eye there. Good eye, both of y'all. Well done. Careless mistakes. Yeah. When you're doing this on your own, you're not going to have me there to commentate you through it. Okay? And what do you mean do it on your own? I'm going to tell you tomorrow about a bonus opportunity that's worth 10 points on your test grade. Doing this for tangent of pi 30 seconds. This is only for tangent of pi 8s. Okay, now we're almost there. Notice in the denominator, we now have Looney. Now, Looney, we have conjugates. So how do we get rid of something plus the square root of 2? Something minus the square root of 2 in the top and bottom. And in the bottom, by design, you're going to get 2 times 2 is 4. Inner and outer cancel. Square root of 2 times square root of 2 is 2. So you get 4 minus 2. And in the top, let's go ahead and multiply the radicals under the radical first. If we expand these conjugates, we're going to get 4. They're not conjugates, actually. They're the same. No, they should be conjugates. I miscopied. See, there's a lot of little places here where little things can go wrong. This should be 2 minus the square root of 2. And so that's going to give you 2 times 2 is 4. Inner and outer cancel. And you're going to get minus 2. And then all of that is going to be times 2 minus the square root of 2. Hang in there. We are so close to finishing. All right, so in the top, after we expand these conjugates, we're left with that. Pretty impressive. 4 minus 2 is 2, so we're left with the square root of 2 times 2 minus the square root of 2, all over what? 2. Okay, so we've met the first two requirements. We don't have any radicals under a denominator or in a denominator, and we don't have any fractions in a radical, but we still have it factored, right? It needs to be expanded out. That was one of the rules, okay? Expanded out. So we have one last little task here. If I distribute the square root of 2, I get 2 square root of 2 minus square root of 2 times square root of 2 is 2 all over 2. And now I can split it up, 2 square root of 2 over 2 minus 2 over 2, and good things will happen. We get the square root of 2 minus 1. And wasn't that worthwhile, doing all of that wonderful radical algebra to get down to something that's so beautiful? Square root of 2 minus 1. And that's tangent of pi eighths. Now let's see. I caught a couple of mistakes. Y'all caught one mistake. I caught another mistake. It's easy, which is why these problems are so good. They force you to kind of pay attention to detail. And in today's day and age where everything's moving so fast and everything is just so accessible, you know, our attention spans go away. So being able to sit and focus and sustain concentration, that's a great task, okay? That's what I kind of spoke about in the NHS speech here. There they are. Square root of 2 minus 1 is tangent of pi eighths. Isn't that amazing? Okay, so I'm just going to mention the bonus, which we'll go over tomorrow. That was doing it for pi eighths. If you choose so, worth 10 points on the test, which might be a week from tomorrow, the 21st, Tuesday the 21st. That's when it's due. On a separate sheet of paper, you're going to find the simplified exact value of tangent of pi 30 seconds. Tangent of pi 30 seconds. This is the Mr. Peck problem. Mr. Peck used to give this as a bonus way back in the day. And it's such a great problem. I would think if you could sit down and do this in one sitting in front of me, you deserve 100 for the entire second semester. It's that good of a problem. What it requires, using those three rules, no fractions under a radical, no radicals in the denominator, and expanding it all out. If you could do it live in front of me, you've got everything that you need from this semester in your head. You've practiced and you've mastered it. You don't have to do it in front of me live. You could do it at home off to the side. All you have to do is on the day of the test, you turn it in, and then when the time comes, you have to show it to me on your calculator that you've typed your expression in and show me that it equals the decimal, just like we did right here with pi eighths. You're going to have it all typed in, and you're going to have that, and you're going to show me that the two numbers are the same. If you do that, it's worth 10 points. There are a lot of people for Ms. Skurhawk. They're testing today over what y'all are going to test over next Tuesday. So they're about a week ahead of us. And they've been trying this and trying this. So every year about maybe 3 or 4 people succeed at turning stuff in. There's no prorated points either. So if you get a good star but you mess up, it's 0 points. It's all or nothing. Okay? So good luck. I don't even know if it's on the internet. I don't think so. Maybe on Reddit. I don't know. Can you hire someone to do it for you? Sure. Does that defeat the purpose? Absolutely. Okay. But make sure you focus on the credit before you focus on the extra credit. But notice this works kind of the same way because pi 30 seconds is 1/2 of pi 16ths, right? But pi 16ths, which is not on the unit circle, is 1/2 of pi eighths. And of course, pi eighths, as we just saw, is 1/2 of pi fourths. So you are going to have, and I'll work pi 16ths with you tomorrow. I'll actually work that one in front of you, and I'll show you what it looks like. It'll be a little bit more fun than what we just did with pi eighths. And if you think that if I do tangent of pi 16ths for you, I'm practically doing tangent of pi 30 seconds, oh, you are so wrong. There's an exponential difference between pi eighths and pi 16ths and pi 16 and pi 30 seconds and pi 30 seconds and pi 64ths. I've never assigned that one. But yeah, every time you do it exponentially, you get more and more radicals. So anyway, it's kind of fun. It's worth 10 points. So we're done for the day. I don't think there's any announcements. So any questions? Y'all can pledge on your own today.